everyone. Just before I get started, I just want to get an idea of who's in my audience. So how many people here are in first year? Okay, I see a few. How many in second year? Okay, the rest of you are obviously in years 3 or 4. Okay, so the rest of you will definitely be able to follow. First years, I've done my best to make this accessible to you as well. So hopefully you'll be able, hopefully everyone in this room will be able to take something away from this talk. I'm assuming nothing beyond a basic understanding of linear algebra, but as we know too well, the word basic means different things to different people. Anyway, let's start off by talking about orthogonal transformations. Okay, so I think we've all seen the definition of an orthogonal transformation. An orthogonal transformation of Rn is a linear map whose transpose is its inverse. So such a linear map, you can also see the determinant is plus or minus 1. And orthogonal transformations, the way we characterize them is that they normally preserve lengths and they preserve angles between vectors. Okay, so the idea is if you have an orthonormal basis, it remains an orthonormal basis. It might be a different basis, but it's still an orthonormal basis after this transformation. So a classic example is rotations of the plane. So if you have something that looks like this is the plane that we all know and love. If you rotate it, that is an example of an orthogonal transformation. Okay. The thing is, orthogonal transformations don't always preserve orientation. This is not going to be hugely relevant for us, but something that I want to stress less. So a standard example is reflections in R2 or in R3. So you have something like this. This is R3. I've done my best to represent it two-dimensionally. It's a little clunky, but let's go with it. So if I were to do this reflection, obviously that's not going to preserve the way that things are oriented. This is still orthogonal transformation. There's another interesting class of orthogonal transformations in R3, which is rotor reflections, which are essentially where you have a rotation on one plane, but a reflection everywhere else. So this is also valid. This is quite an interesting thing. But yeah, this is just to give you an idea of what these orthogonal transformations look like. So there's also the so-called orthogonal group. Now, I'm aware there are some first years you might not have seen the concept of a group before, but that's not hugely relevant. Essentially, wherever I use the word group or subgroup or something, you can replace it with the word set. And it's not going to be hugely different for the purposes of this talk. They are very different things, but not going to be hugely relevant for this talk. So for any n, the orthogonal transformations together form something called the orthogonal group, because the composition of two orthogonal transformations, orthogonal transformations, so on and so on, by definition, they have inverse, and you can work out the rest. So this group is usually denoted ON of R. You might denote it ON of C if you're about orthogonal transformations of complex spaces, but yeah. So this is the orthogonal group in n dimensions. So essentially, by which I mean it acts on Rn. So for example, O2 of R consists of precisely rotations and reflections. You can prove that essentially an orthogonal matrix with 4 elements, 2 rows and 2 columns is going to have determinant either +1 or -1. If the determinant is +1, you can prove that it's a rotation. And if the determinant is -1, you can prove that it's a reflection. So in 2 dimensions, you have a very precise characterization of the orthogonal group. And all O of R consist of rotations and reflections, but as we saw on the previous slide, they might also contain more complicated objects. Really, the goal of this talk is to try and understand some of the transformations that live in O of R. And we'll be looking at specific subgroups of O of R. Okay. But yeah, the key takeaway from this paragraph is that you have rotations and reflections in all dimensions. And actually, we're going to be very interested in reflections. Okay, so there's 3 types of subgroups that we're going to care about. First is finite subgroups. Okay. because finite things are nice. The second is effective subgroups. I'll tell you exactly what those are in a minute. Okay. And the third is subgroups generated by reflections. So let's see exactly what these terms mean. So a finite subgroup is exactly what it sounds like. It's a subgroup of O n of R, which only has finitely many elements. Okay, and there are plenty of examples. We'll see some in just a minute. Before that, I want to define effective subgroups and subgroups generated by reflections. So an effective subgroup. So we say that a subgroup acts on Rn effectively if it only fixes the zero vector. Okay. So in general, a reflection will fix, well, a reflection will always fix anything that's orthogonal to it. So if you have just one reflection in a group, that's not going to be an effective subgroup. Okay, if you have a group that's just generated by one reflection, a group of order 2, that's not going to be effective because it's going to fix a bunch of things that are orthogonal to it. Okay, so the idea is an effective subgroup is something where the only thing fixed by all of the elements together. So, I mean, you could have subgroups that are effective, which contain reflections in them, right? But the point is that if you have more than one reflection, then one reflection might fix something orthogonal to it, or will fix something orthogonal to it, but another reflection in the group might not. So that would make it effective. Okay, the effective subgroup is something where the only element fixed by absolutely every single one of the elements of the subgroup is a zero vector. And then you have subgroups generated by reflections. Again, it's exactly what it sounds like. It means that all elements of such subgroups can be expressed as products of reflections. By product, I mean compositions of reflections. So examples, if you take a subgroup, this is basically a cyclic group of order 4, which lives in O n of R. It's basically like, you can think of it as just all 4 of these rotations together, 90, 180, 270, and 360. So this is an example of a finite subgroup because obviously it only consists of 4 elements. Okay. An example of effective subgroups is the group SO2 of R, which consists of all elements of O2 of R of determinant 1. In other words, it's going to be every single possible rotation of the plane. So this is not a finite group because there are infinitely many rotations that you can do to the plane. And actually, all of those rotations put together form this group. And the action of that group is effective because the only vector that is fixed by every single possible rotation of the plane is 0. Then you have subgroups generated by reflections. And an example of this is just a group of order 2. If you just take the plane and you just look at 2 elements, one is the identity and the second is flipping around the vertical axis. This is a group of order 2. This is obviously generated by reflection because everything in that group, there are only 2 things in that group. One is the identity, which is the product of the reflection with itself, and then there's a reflection, which is just itself. So interestingly, some of these examples are examples of other things as well, right? So this guy is both finite and effective, right? But it's not generated by reflections because there are no reflections living in here. Everything in here is a rotation. They're all of determinant 1. A reflection is something of determinant -1. This does not have it. So this is not generated by reflections. This guy is effective, but it's neither finite nor generated by reflections. Again, it doesn't contain any reflections. And obviously, there are many different ways of rotating the planes. There are infinitely many. This guy is obviously finite, but it's not effective because it fixes the thing that's orthogonal to it. It fixes the y-axis and fixes everything on the y-axis. So it is not effective because those guys are not all the zero vector. A Coxeter group, which is what this talk is about, is a subgroup of O n. It is all of these things. So it is finite, it is effective, and it's generated by reflections. So that's what a Coxeter group is. Okay. So I think this is a little abstract. So why don't we look at a very concrete example in 2 dimensions, which is the symmetries of the equilateral triangle. Yeah. So the group of symmetries of the equilateral triangle is usually denoted A2. Okay, when we think of it geometrically, the reason for this will become apparent, hopefully, towards the end of the talk. All right, so let's draw the triangle. Okay, So we have an equilateral triangle ABC. We have these gray lines through them, through these which go from each vertex to the midpoint of the opposite side. And the point is that if you reflect about these, you get back the triangle, right? So A2 consists of exactly 6 transformations. One is the one where you don't do anything. There are 3 reflections about these gray dashed axes, and there's 2 rotations. You can rotate by 120 degrees, and you can rotate by minus 120 degrees. Because 2 rotations by 120 is 1 rotation by minus 120, and so on. Yeah.
Isn't it that the axis of reflection are preserved by reflection? So why is it bad and effective?
That's an excellent question. So this axis is preserved by this reflection, but it's not preserved by the other reflections. So an effective subgroup is one where every transformation fixes, where the only vector fixed by every transformation is a 0 vector. Okay, yeah. So that's a good question. So just want to emphasize that that's what an effective subgroup is. Okay, so we can clearly see that A is finite, right? And the only one fixed by all of these symmetries is the identity, is the 0 vector, right? And okay, that's a typo. That should be 120 degrees. But anyways, it is clear that, okay, so if you want to show that A2 is generated by reflections, right? Obviously, there are 3 reflections. There are 2 rotations. And one of those rotations is the inverse of the other one. So you only need to show that that rotation is the product of 2 reflections. This should be 120. Apologies. All right. So that we just swapped A and B. We just swapped B and C. So essentially, we performed 2 reflections here. We reflected about this one and then about this one. And what's happened now is we've actually cyclically permuted A, B, and C because A was over here, B was over here, and C was over here. Now A is over here, B is over here, and C is over here. So effectively, what we've done is we've performed a rotation of this triangle by 120 degrees. So clearly, this rotation is a product of 2 reflections. Okay. Therefore, you can see that this subgroup A2 of the orthogonal group in 2 dimensions is generated by reflections. So it satisfies all 3 criteria, making it a Coxeter group. Excellent. And by the way, A2 is just S3 for those of you who know what that is. All right. So let's take a closer look at the 3 reflections of A2. Okay. So the reason why we're going to take a closer look at this will become apparent in a minute. It's because the broad goal of this talk, okay, which is probably something I should have stated at the very beginning, is to not only understand Coxeter groups and look at what they actually do, but to classify them. So there's actually a detailed classification whereby we can talk about exactly what any Coxeter group looks like, which is pretty powerful. And the way to do that is to introduce something that we're going to see. So the reflections don't just generate, right? So the idea is we want to capture the information about a Coxeter group in a simple manner. And for that, we know that it's generated by reflections. So a logical place to look is those reflections, right? So that's what we're going to do. So consider these 6 blue vectors. Okay. So the thing about these vectors, right, is that if you reflect across a gray axis, each of these vectors will get mapped to its negative. So that's what these 6 vectors are. Okay. So you reflect about this, you see, so there's actually one gray dashed line on the y-axis, which you probably can't see. So that sends this guy to its negative, right? Similarly, reflecting about this one sends this guy to its negative over there, and so on, right? So that's what these blue vectors are. And we actually have a special name for them. We call them roots. Okay, so a root is something where is some vector that a Coxeter group sends. So it's like so any reflection will send some vector to its negative, right? So roots of a Coxeter group are precisely the vectors that are sent to their negatives by the reflections in that Coxeter group. Okay, so that's what these blue vectors are. Okay, and there are many examples of root systems. Okay, so this is a root system that we call B2. Okay, so again, what this corresponds to is actually the symmetries of a square. If you take a square, you can think about all the ways to transform it, and actually that's something that's generated by reflections. You can prove. If you look at the vectors that are sent to their negatives by the reflections that live, by all the reflections that preserve the square, that's precisely these ones. If you draw a square over here, then sort of flipping about one diagonal will take this to its negative. Taking one side to its opposite side will take this to this one, and so on. So these are the vectors that are preserved by all reflections that preserve this, that are sent to their negatives by all reflections that preserve the square. So similarly, we have something here that's called A1 cross A1. So this is actually the symmetries of a line. So if I were to take a line here, just draw this line, and look at ways to kind of preserve that line, the reflection that preserve it is one, you just flip the line across itself. Second one is you just flip everything that's orthogonal to the line. And that gives you A1 cross A1, which is another example of a root system. The third, this is a slightly more complicated one. If you just ignore the fact that these roots have different lengths, and the lengths of the roots are something that I'll talk about towards the end of the talk. They're not hugely relevant for like 85 to 90% of this talk. But if you just ignore the lengths of the roots, then this would be the symmetries of the hexagon. Actually, yeah, it doesn't matter that they're different lengths. But yeah, if you were to draw a hexagon, you look at the reflections that preserve the hexagon, it's going to send these blue vectors to their negatives. So that's the G2 root system. Okay. There are many examples, and not just in 3 dimensions. In 2 dimensions, you have examples in 3, 4, 5, n dimensions. Okay. So I just want to talk a little bit about root systems first, because they're going to be very relevant to everything that I have to say. So these root systems are rank 2. What do I mean by that? I mean that they live in R2. They live in a 2-dimensional space. Okay. So the subscripts also add up to 2, and this is not an accident. Okay. So if we look at something like this, right, this is the plane embedded into R3 with the A2 root system on it. And actually, this is no longer a root system. Right? The reason why this is not a root system is because if you look at the reflections that send this one to this one and this one to this one, they all preserve the z-axis. So if you want to look at the group generated by all of these reflections, that's not a Coxeter group. It's not effective because it preserves an entire axis, right? So the thing is, right, if I were to now draw a vector, so I've now drawn a vector here, that's on the z-axis. Maybe it's not clear that it's on the z-axis, but it's meant to be. Now, this is a root system. Because now, if you look at the reflection that sends that to its negative, and you add that, and you look at the subgroup generated by all of those reflections, that is effective. So this is now a root system, and it's actually called A2 cross A1. Okay. So a key takeaway is that a root system must contain a basis of the ambient space, because if it does not contain a basis, which this did not, right? Before we added this, it did not contain a basis of R3. So when it does not contain a basis of the ambient space, if you have something, you can essentially look at all of those reflections, and they're going to preserve the thing orthogonal to it. And you know that there's something orthogonal to it, which is kind of not reflected in the root system, which does not appear anywhere in the root system because it does not contain a basis. Okay. So yeah. So I said that our idea was to classify Coxeter groups, and now I'm going to explain what the relevance of root systems is to this classification. Okay. So perhaps you saw this already, but there is a very direct correspondence between root systems and Coxeter groups. Okay, so if I have a Coxeter group, what I walked you through so far was how to get a root system from a Coxeter group, right? Essentially, a Coxeter group has reflections. You just look at the roots of those reflections. That's a root system. Okay, and in fact, in this talk, I didn't even define a root system properly. You can basically just define it to be the roots of a Coxeter group. But there might be other definitions of a root system that you've seen before. especially if you've taken a course on Lie algebras, you probably have, like the way Andres Paul explained root systems was not like this. Okay, it was still a good explanation, but it was not this. So you can actually show the notions are exactly the same. And yeah, so if you want to go from a root system to a Coxeter group, it's actually even easier than what I explained. Because to go from a root system to a Coxeter group, just literally just look at all of those reflections and look at the subgroup generated by those reflections. That's a Coxeter group. So it's even easier to go the other way. So there's a very direct correspondence here. So the idea is every root system is a product of irreducible root systems, which is both that A1 cross A1 and A2 cross A1 stuff. Okay, so I'll explain irreducible root systems in a minute and what it means to take a product of two root systems. But the idea is essentially to introduce, the idea is essentially just the same as taking direct sums of two vector spaces. You have one basis, you have another basis. You can look at the space spanned by the first one, space spanned by the second one, take the direct sum. And what happens is that everything spanned by the second basis is orthogonal to everything spanned by the first basis. You can just, it's essentially the same construction. Not essentially, it is the same construction. But we'll come to how that is relevant in a minute. So the idea is to simplify the information contained in a root system, right? Because we have a lot of roots in general. I mean, we have A2 over here, it only has 6 roots. But as we can see, we can do even better than 6. So we have positive roots first. Okay, the idea is to extract 3 roots, which, so the idea, the reason why we use the word positive will be clear in a minute, but the idea is that you essentially look at non-negative linear combinations of these guys, and the only vector that also lives is this one. From this, you can do even better. You can extract the so-called simple roots, okay, which is just these two. And do you remember how I said on the previous slide that a root system must contain a basis of the ambient space? This is the basis. The simple roots of a root system, which I will show you how to get, are exactly a basis of the ambient space. Okay, and they actually have a lot of deep properties, which we will exploit to classify Coxeter groups. Now, this next bit is where I think the true ingenuity of this classification really comes to play. Because the idea is, well, when you have simple roots, right, you're still looking at guys that live in some sort of vector space. You're still trying to deal with them geometrically, perhaps algebraically. It turns out that you can deal with them combinatorially, which is pretty cool. And the way that you deal with them combinatorially is by constructing these objects known as Coxeter graphs from simple roots. So those of you who've studied Lie algebras before might have heard of Dinkin diagrams. Coxeter graphs and Dinkin diagrams are very closely related. They're almost the same thing. So this is what a Coxeter graph looks like. It's actually a very simple graph in this case. That is the Coxeter graph of A2. And using Coxeter graphs, you can classify irreducible root systems. And once you've classified irreducible root systems, you've classified root systems because any root system is a product of irreducible root systems. And then you've classified all Coxeter groups because the correspondence between the two. Yeah.
And the products unique.
Yes, because it's essentially like the direct sum construction. So, yeah, well, unique in the sense up to isomorphism. Yeah. So, yeah. So simple roots. All right. So let's look at how we can extract the simple roots. Okay. So the informal idea is, as I said, we want to encode all the information about a Coxeter group using just n vectors. So it's acting on Rn. So you need at least n pieces of information. Otherwise, you're just losing information. So here's a root system. Here's V2. The idea is to pick n roots such that the angle between them is as large as possible. Now, just a word of warning. Perhaps I didn't choose the best possible numbering here because I just numbered them this way because there are 8 roots. But actually, n over here is 2 because n is the dimension of the ambient space. Okay, so n is not 8, n is 2. Perhaps I shouldn't have numbered the roots. But anyway, let's roll with it. So if you pick these two, if you pick R1 and R4, okay, that's why I numbered so that I can remember. So if you pick R1 and R4, then these are 2 vectors. Right? And actually, the angle between them cannot possibly get any larger. Well, you want them to also be linearly descending. this and this, it's essentially the same root, right? Because they correspond to the same reflection. So that's not giving you any information. The idea is to, if you haven't phrased that as precisely as possible, I'll give you a precise way of picking simple roots on the slide after this. Okay, so this is like a more of a discussion. So anyway, so these are the simple roots. Okay, so if you think about this, you cannot get an angle any larger than 135. Except for this, we don't know about that. And we call these the simple reflections. So we call these the simple roots. Now, these simple roots correspond to certain reflections. Those reflections are called the simple reflections. And actually, those reflections generate the Coxeter group in question, which is kind of cool. Yes?
Can we pick the angles so that they are small as possible?
That's an excellent question. That's actually answered by this. Because if you pick this one and this one, so that the angle is as small as possible, that will also generate the Coxeter group in question. But actually, that's essentially the same as picking these two, because picking R1 is no different from picking R5. So you pick R1 and R2, that's the same as picking R5 and R2, and get the angles as large as possible. Okay. So the reason why we pick the angle to be as large as possible is because we want to maximize the number of roots that are non-negative linear combinations of these two. Because that's how you kind of, so this is kind of the motivation for what I'm going to show you on the next slide, which is a precise way of picking simple roots. Okay, so are there any questions about this before I move forward? Are there any questions about everything I've done so far? Yeah?
So visually, I code generated by positive roots,
Yeah.
using those that generate new codes.
Yeah.
The most ones.
Exactly. You're trying to generate a cone that's as wide as possible.
So in 2 dimensions, it's almost like obvious that there's only 2 you can pick, but in 3 dimensions and higher, how is it certain that there are only 2 or only 3? So
that's a good question. So I will. So the idea, right, is so actually it does take some work to show that. So the idea is there is a criterion for linear independence, okay, that you can show, which has to do with inner products. And the idea is that in this case, the inner product of R1 and R4 is negative. Okay, so there's a criterion that you can use to show that actually when you do the construction, I'm going to show you in the next slide, then the inner products between the roots, between the simple roots are all going to be negative, and you can then show that they're linearly independent. You can also show with the span space that there's 10 of them. Okay. So, okay. So simple roots in terms of positive roots. So there's a more direct way of picking them. I don't know if it's more direct, actually. I don't want to include that line, but it is another way. It's more precise, I think. So actually, I should probably have stated this at the beginning as well. But all of this is based on a module that I did last year. So last year, I did an exchange program. I'm on NEM side with the year abroad. I did my year abroad in EPFL in Switzerland. So this is based on the module that I took at EPFL on Coxeter groups taught by Anna Luchowska. So this is based on that module and the lecture notes for that module, which were written by some students. So anyway, so the idea is, okay, so let's draw some vector t, which is not in the root system. Okay, you can do this in any dimension. Okay, so because you know that there are only finitely many reflections, so you know there's a vector that's not in the root system. So just pick some such vector. The vectors whose inner product with t is positive are the positive roots. Okay, hence the word positive. Remember earlier, you go from the root system to the positive roots to the simple roots. So we're first going to pick the positive roots, and then we'll pick the simple roots. Okay. So the guys whose inner product with t is positive live in this region. Okay, you just have to look at the things that are orthogonal to, you look at the line orthogonal to t, and you look at everything that's above that line, and those guys are going to have a positive inner product with t. And the n vector such that all positive roots are non-negative linear combinations of these simple roots. So if you just pick n vectors over here, such that everything that lives in this green region, all the roots that live in this green region, are non-negative linear combinations of those n guys, then you're going to get precisely the simple roots. Okay, so that's how you know that there's n of them. I've kind of cheated a little bit over here. There's a few details over here. Yeah, so anyway, so you can, let me just finish talking about this and I'll mention what details I kind of glossed over. So it turns out that the angle between these guys is maximum, and you can show that it's in fact always obtuse, by which I mean the inner product of the roots is always negative. Or rather, I shouldn't say negative, I should say non-positive. Okay, so it's 90 or obtuse. And one can show that for all choices of t, you get something that's equivalent, because if you were to take t, if you were to take t somewhere over here, then you would get this one or something. I don't know. So you'd get something like that. So the root system still, I mean, not the roots, the simple roots still look exactly the same. And actually, what we care about more is the angle between them, because also don't forget we have rotations in this, but you can always kind of map one to the other. So it doesn't actually matter what t is. So the thing is, right, it actually takes a lot of work to show that the simple roots, if you construct them in this manner, have the properties we desire. So one of the properties we desire is that their corresponding reflections generate the Coxeter root in question. That's not an easy thing to prove. Second thing that we want to prove is that they're a basis. That's easier to prove. And as I was telling Arif, the key ingredient there is the criterion for linear independence that has to do with inner products between these sets. But again, over here, things are quite clear because I've drawn it out and it's in 2 dimensions, but you're usually working in Rn. You're working with a root system where there are going to be n simple roots and a whole lot of roots. Like sometimes it's like hundreds of roots. So it's generally not so easy to show these properties. But I'm going to gloss over those details because that was like, I think 2 weeks of the module. So I'm not going to do 2 weeks of a semester-long module in a 1-hour talk. Okay, so yeah. So now we can talk about what irreducible root systems are. And we've already talked about it quite a bit. But as I said, they can be put together in a natural way. You just consider, so I'm going to do it by an example, right? Because I'm also aware that there are some first years here. I don't know if you know what a direct sum is. You don't need to, it's essentially an extension of what I'm going to show you. So consider the one-dimensional root system. There's only really one root system in 1 dimensions. There's only one possible reflection of the line. So the idea is we combine it with itself. Right? So you take root systems in smaller dimensions and you use them to build root systems in higher dimensions. Okay. So you can combine this with itself by just adding an orthogonal component, right? So essentially you just do that. Okay. And this is a combination of A1 with itself. You have A1 on the x-axis, you have A1 on the y-axis as well. Okay. And you can just combine, you can do exactly what I said. Right? You combine root systems in this manner by essentially just, the idea is to just do the direct sum construction. If you just look at the space span by one set of roots, by one root system, you look at the space span by the other root system, take the direct sum of those, the basis, the union of those two is going to be a basis of that space with the desired orthogonality properties. So root systems that are made up of smaller root systems are called reducible, and root systems that are not are called irreducible. If you want a precise characterization of irreducible root systems, this is what it is. You essentially should be able to separate the roots into 2 disjoint orthogonal subsets. When I say orthogonal subsets, I mean everything in one is orthogonal to everything in the other. Okay, so I think that should be fairly clear. Now we can, before I move on, any questions about what I just did? No. All right. If at any point any of you have questions, then please just shout out as you have been doing. All right. So angles between simple roots. So simple roots have a lot of fascinating properties. Okay, and one of them has to do with the angle. So let's first fix a root system. We'll call it delta, and we're only going to look at the simple roots because it turns out that that's all we need to look at. Okay, so again, we're going to stick with our friend V2. Okay, so we have the 2 simple roots R1 and R2. We saw earlier how to pick these guys. Yeah, so here I have the first sort of, well, a lot of things I've said are non-trivial, but this is the first thing that I kind of stated explicitly and outright. For all I and j, there exists a Pij such that this is true. And the thing that I want to really stress is that this Pij is an integer. Okay. So essentially the idea of this Pij is, if you look at this guy, right? This is going to be 5 over. This is going to be 5 over 4. It's that 4 that we care about. Okay. You're essentially extracting, what you're doing is you're extracting the order of, if you take these two simple roots and multiply them together, you're actually going to get a rotation. And what you're doing is you're extracting the order of that rotation. Okay. You can prove that this is the order of that rotation. It's again not a trivial thing to do, but you can prove that. And in fact, using that fact, you get a special presentation of all Coxeter roots, which I'm not going to talk about here. But there is this thing called Coxeter's theorem, which gives you that. But yeah, so what this is essentially, this is just the inner product, the dot product. The dot product is this times the cos of something, right? And that's going to be the cos of something that lives over here. So it's a negative thing, and it's pi over something's going to be pi over whatever this is. Okay. So it's a fairly natural result when you think about it visually in 2 dimensions. It's not maybe so easy to think about in high dimensions, but that's fine. Yeah, so in this case in B2, which is the root system depicted here, P12, because there are only 2 roots, right? There are only 2 simple roots. P12 is 4. Okay. And these guys encode information about the angles, right, in a very simple way, right? Because you don't want to have weird complicated numbers. So just simple 4 suffices. So here's another non-trivial result. You take a matrix. Okay? So to a Coxeter group that's acting on Rn, you can associate an n by n matrix. And the entries of that n by n matrix are going to be these guys. Okay? These cos minus cos of whatever. And that matrix is, I think it's fairly intuitive to see that it's symmetric because the angle between 2 things does not depend on the order in which you look at those 2 things. So that's the intuition for why this matrix is symmetric. But it's not at all obvious that it's positive definite. And to show that it's positive definite, you need something called Sylvester's criterion for positive definiteness. I'm not going to do any of that here because it's a non-trivial criterion and it takes some work to prove that the criterion is true before you can even apply it in this case, and then it takes some work to apply it. So I'm not going to do any of that. I'm just going to say this matrix is symmetric and positive definite. Now, it's not hugely important as to, actually it is hugely important as to why this is symmetric and positive definite. But from, like, as far as intuition is concerned, it's not the most important. This actually is a very important step in the classification, which I will talk about. So now we're ready for our final ingredient of the classification. So if you remember, I said we start off with Coxeter groups, then we have positive roots. You have Coxeter groups, you have root systems, you have positive roots, simple roots, and then Coxeter graphs that you construct out of these simple roots. So we're nearly at a point where we can classify them. And actually the idea is to do the classification entirely using the rules of Coxeter graphs so that you do not have to think about geometry in any way. Yeah. You only use the rules of Coxeter graphs and a little bit of linear algebra to do it. So what is a Coxeter graph? It's actually kind of tailor-made to the idea of Coxeter group and the idea of simple roots and whatever. So it's just a graph on indirect, it's just an undirected graph on n vertices, such that every edge has a weight of some sort. It has a coefficient associated with it. And actually, we have this weird thing where if the coefficient associated to the edge between 2 vertices is 2, you simply don't draw an edge. And if coefficient is 3, you just leave the edge unlabeled. And if it's 4 or something greater than 4, then you label it with that number. And the reason why this is the case is because in the practical classification of Coxeter groups, we separate things. We separate things where the coefficient is 2 because of the irreducibility thing, and we don't label things where the coefficient is 3 because we're going to see a lot of 3s. So I think there was a question.
Is it the type of Aij small?
There is not. That is not right. Oh, well. Yeah, okay. The point is that when Kij is 2, these guys are not there. So I guess you could say Kij can be sure. Yeah.
Does it mean that a Coxeter group is irreducible if only if its graph is connected?
Absolutely. Absolutely. And that's something that I'm going to talk about on the next slide. So yeah, so as you can see, this is quite tailor-made to Coxeter groups because of that reason. and another reason as well. So this is an example of a Coxeter graph. This is actually the Coxeter graph of an irreducible Coxeter group. Okay. This is another example of a Coxeter graph. This is the Coxeter graph of a reducible Coxeter group. Technically, by our definition, this is also a valid Coxeter graph, but this is not the Coxeter graph of any Coxeter group. It's just, yeah. Okay. Because we will need to impose another small condition on Coxeter graphs in order for it to suffice to simply classify those graphs, to classify the groups. Okay. I honestly don't know if there is a specific reason why we don't include that condition in the definition, but I guess you just want to maximize generality. But this is just how it's done. So, but we're basically not going to care about these endpoints like one. Okay, so for every Coxeter group, we can construct a Coxeter graph, just make the vertices the simple roots, and just make these coefficients the Vij's that we saw on the previous slide. So in other words, to recap what the Vij's are, they're going to be the order of the rotation that you get by kind of composing those two reflections together, or you can just simply think of it as the angle, as having to do with the angle between them. So are there any questions about what's on the slide? Because there is a lot of information here. I'm basically bombarding you guys with definitions. So stop me if it gets unclear. Yeah, I shall assume from that silence that this is clear. Graphs from groups. Okay. So we're going to look at some examples because, as I said, I was just bombarding you with definitions, and I don't like it when people do that. So I'm not going to do that either, at least not without some examples to illustrate what I'm bombarding you with. So we have our good old friend P2. Okay. Can anyone guess, first of all, how many vertices this Coxeter graph is going to have? 2. Yeah, it's going to have 2 vertices because there are 2 simple roots. Okay. So it's going to look like this. Now, is there a number that should be on that edge? There may or may not be a number. I'm seeing people gesturing. I think, yes, you're right. There should be a 4 over there. The reason why there should be a 4 is because the simple roots are this one and that one, right? So the angle over here is pi over 4. That's where you get the 4. Okay. There's another example, A2. So any guesses as to how many vertices this guy has? Again, 2. Right? Just going to look at this. And is there a number on top? There's not a number, exactly, because over here, this is a pi over 3. So we have a 3, but we don't label things with a 3. And the reason why we don't label things with a 3 is because when I get to the actual classification, there's going to be a lot of 3s. Okay. So finally, we have, well, not finally, we have 4 examples over here. We have A1 cross A1. Any guesses as to how many vertices this one has? Again, 2. Now, are they going to be connected? They're not going to be connected, right? Because the 2 simple roots are going to be like I hat and J hat, E1 and E2. They're orthogonal. So there's no line between them, because if we had a line, we would label it 2, and by convention, we just skip that. Right? So, okay, and G2 finally. This is a slightly more complicated one. Any guesses? So, yeah?
6.
Yes. Exactly. 2 vertices in a line with 6. Because as I said earlier, this is like a hexagon, right? So, yeah, precisely. So hopefully this sheds some light as to how to construct Coxeter graphs from root systems. Okay, so just a little more on Coxeter graphs. Okay, this is just sort of random trivia, so I'm going to breeze through this because not all of it is hugely relevant. And I also want to talk a little bit about the classification. The thing is, right, before you get worried about time, I'm not going to prove the classification because that is a long, long, long proof. I'm just going to tell you what it is. Okay, so this is, yeah. Yeah.
We'll continue with the geometry first. Is it right that you're only using plane-based reflections? For example, in R3, you're not using the reflection which maps every vector of the space to its negative, which is like a composition of 3 reflections.
Yeah.
It's part of the orthogonal group that has and the -1.
Yes, okay.
But it doesn't count in your reflection because you only consider plane-based reflections. So, right?
I'm considering reflections across a plane. Yeah,
Okay,
yeah,
thank you.
that makes sense. Yeah,
That's
yeah, yeah, yeah. So in R3, an example of a reflection in the sense of what I'm doing is, so I think what you're talking about is a rotor reflection.
Yeah, but
I think it's a rotor reflection thing that you're talking about because it's like you take the z-axis, you send it with negative, and then you take x and y, you send them to minus x and minus y.
yeah, which is that reflection. I mean the rotation as well. Yes. Right.
Yeah, yeah, but it's like somehow it's not quite right because everything that lives above the plane or below the plane is sent to its corresponding point above or below the plane. Everything in the plane remains in the plane, kind of it goes around the origin. So it's a rotor reflection. It's not quite a reflection. A reflection would fix everything orthogonal.
It's also a composition of three reflections.
I suppose it is. Yeah. Yeah. The rotor reflection.
Yes. Yeah, that's
Okay, cool. Any more questions? Okay, no, all right. So to every Coxeter graph, so just as I said, you can associate a matrix to every Coxeter group. You can associate a matrix to every Coxeter graph. It's exactly the same matrix when the Coxeter graph comes from a Coxeter group. Yeah. And again, this is symmetric, right? Because the graphs are undirected, you don't care about whether I look at Kij versus Kji, right? Talk about two different. So such a matrix is positive definite. When such a matrix is positive definite, because as I said, we've allowed sort of this arbitrary construction of Coxeter graphs, right? When such matrix is positive definite, we say that the Coxeter graph is also positive definite. And similarly, in the classification, you often look at subgraphs of Coxeter graphs and you look at their determinants. I'll talk about what a subgraph is, but the determinant of a Coxeter graph is just the determinant of this matrix. A subgraph is something that you get when you either remove a node and its adjoining edges, or when you decrease the weight of one of the edges, and by which you can also remove an edge. You turn a 3 into a 2, get rid of the edge. And that's another reason why you don't label things with a 2, because you can't go from a 2 to a 1, because there's no edge. And anyway, so now we have a correspondence of properties, which is exactly what my friend over there remarked in the first row. So irreducibility of a Coxeter group corresponds precisely to the connectivity of the corresponding Coxeter graph, right? So a Coxeter group is irreducible if and only if the Coxeter graph is disconnected, is connected. And if it's reducible, if it can be made up of multiple root systems that are kind of joined together orthogonally, then because orthogonality results in no edges, the Coxeter graph is going to be disconnected. Similarly, we saw that this matrix is always positive definite, and that means that the Coxeter graph of a Coxeter group is always positive definite. So therefore, it suffices to classify connected positive definite Coxeter graphs. And if you can classify these graphs, then you have a classification of irreducible root systems. And when you have a classification of irreducible root systems, you have a classification of irreducible Coxeter groups, and therefore of Coxeter groups in general. Okay, so I hope the train of thought here is clear. Is everyone happy with this? Okay. So
is that why the, for example, the graph that didn't work out wasn't the group?
yeah. Yeah, exactly. Yeah. So here you have it, the big result. Okay. This is every single connected positive definite Coxeter graph in existence. This is all of them. Okay. As you can see, there's quite a lot of them. Okay. I'm just going to spend a minute or two talking about what some of these guys actually are, because this is the notation that was used in a book. So that was the book, that was the primary reference to this module. Okay. And it's not that I couldn't have made these by hand, I didn't want to. Right. Yeah. So you have these guys, AN. So this is why I said the 3 is going to come up a lot, because you can see there's a lot of guys with unlabeled edges. There's 3s everywhere, right? You have 120-degree angles in a lot of places, which is quite interesting, right? So AN are precisely the guys where all of these guys have sort of 120-degree angles between them. But in 3 dimensions, like this guy and this guy are orthogonal, right? This is not a triangle. This guy and this guy are orthogonal. These guys have a 120-degree angle. These guys have a 120-degree angle, right? Bn is a little more interesting. You have this sort of the square kind of thing going on one plane, and then you have the same thing as an going on the others. Dn is a little weirder, especially because it's only non-trivial in dimension 4 and above. So what H2n is it's the dihedral group of order 2n. It's the symmetries of the regular n-gon, and the subscript is 2, which means that there are always 2 elements over here, and it always lives in R2. So that's the convention with subscripts. So you have so this corresponds to the symmetries of the pentagon. This corresponds to the symmetries of the 7-gon. You never remember what it's called, the octagon, the nonagon, I think. And we separate the case of n equals 6. So this is the same thing as this, but we separate it and we call it G2. And there's a reason why we call it G2, which I will get to in a minute. And then you have I3, which is some weird guy in 3 dimensions. I don't even know what I3 looks like. I don't know what I4 looks like either. And as you can see, there's a bunch of interesting Coxeter graphs over here. And these all correspond to root systems, to the simple roots of certain root systems, from which you can construct Coxeter groups. And that tells you what these Coxeter groups actually are. Yeah?
Is there a reason why your spinning go?
It doesn't get out to mention it.
Oh.
Yeah. So actually, this is a okay. We'll come to the dimensions 2, 4, 6, 7, 8 in a minute. Okay. So yeah, just marvel at it. It's a beautiful result, and it's actually not that easy to prove, which is why I decided not to do it over here. So my idea for this talk was to kind of give you all an appreciation for what Coxeter groups are, and to give you some idea of how they are classified and the ingenuity of using graphs so that you can use combinatorics to classify them, combinatorics and linear algebra to classify them, instead of thinking about geometry. Okay. So there are no further questions. I'm gonna move on because there's a couple of things I want to. Yeah.
Okay. I don't know which is the tetrahedral symmetries among these. The symmetry of tetrahedral should form a cluster group.
Yeah.
Oh, okay.
So
I probably should point out I3 is probably the recognition grid of Microsoft. Because it's the value.
yeah, probably. Yeah, I think you're right. Yeah. I don't quite remember what all of these are, but they yeah. But you can kind of work this out at some point, and I don't want to. Not now. So anyway, so shall I move on? I'm aware that there's not a lot of time, so I'm just gonna quickly mention a few interesting connections. Yeah. Okay. So there's one specific case that I want to emphasize, which is the crystallographic case. Okay. So before we talk about crystallographic groups, let's mention what a lattice is. So a lattice is, there are many characterizations of a lattice. You can also think of it as a discrete co-compact subgroup, which is the definition favored by many eminent mathematicians I know. But this is how I'm going to define it for the purposes of this talk. Okay. And a classic example is this, right? I'm just going to talk about the Z-square lattice, right? It's just basically all of these points. So it's like you have some basis, okay? It doesn't have to look like this. You could have something that looks like that as well. You could have horizontal lines and skewed planting lines or whatever. And it's basically just you take integer linear combinations of some basis of R, so of Rn, and that's what this is. So this is just integer combinations of E1 and E2. And you say that a Coxeter group is crystallographic if it preserves some lattice in Rn. So it acts on some space. There's a lattice in that space that is preserved by the Coxeter group, i.e. it maps points on the lattice to other points that are also on the same lattice. Then you call that Coxeter group crystallographic. And sometimes you would refer to such groups as Weyl groups. Sometimes you would actually include the data of the lattice as well in the definition of a Weyl group, which is why you care about root lengths all of a sudden. So now we're going to classify crystallographic irreducible Coxeter groups. And actually, we can start eliminating things. It turns out these guys are not crystallographic, which is why we separate the n equals 6 case, because that is crystallographic. That does preserve a lattice. Okay. Similarly, we get rid of this and this. And here, we're left with something that should look very familiar, especially to people who've studied the algebras. Because this is very closely related to the classification of semi-simple Lie algebras over the complex numbers. Now, there are some people who don't know what Lie algebra is, and that's fine. Just listen to me waffle for the next minute or two about this. And this is the classification of crystallographic irreducible Coxeter groups. Okay. So just before that, I want to talk a little bit about the Coxeter plane. Does anyone have any questions, by the way, about this classification? If not, I'll talk about the Coxeter plane. Because as I mentioned, it's hard to visualize some of these root systems. Okay, so Coxeter plane is a much easier way of visualizing them. So I'll just talk very briefly about what this is, and I'll mention the link to semi-simple algebras over C, and then we'll wrap up. Okay, so very quickly, you have these things in Coxeter groups called Coxeter elements. And Coxeter element is essentially a product of all of the simple reflections. Now, there can be many Coxeter elements, right? Because a Coxeter group is not commutative, not in general. Like, I don't think they're commutative beyond A1. So a Coxeter group is not in general commutative, and therefore you can have multiple Coxeter elements. However, it's actually quite interesting to note that all of these Coxeter elements are conjugate to each other. Okay, so they behave similarly within the group. And it can be shown that there exists a unique two-dimensional subspace with any Rn, i.e. a plane, such that on this particular subspace, the Coxeter element acts as a rotation. So if you look at this, so the Coxeter element is something that transforms the entire space. You restrict that transformation to the specific plane, and all of a sudden it's a rotation, which is quite nice. So we call this plane the Coxeter plane of this Coxeter element. Now, in general, the root system is large. In fact, like root systems like E8 have like 200 plus vectors in them. And even the simple roots, like it's 8 dimensions. It's not easy to visualize. So what you can do is you can essentially project these roots, not just the simple ones, but all of them, onto the Coxeter plane, and gives you some very nice pictures. So if you head over to your inboxes and you look at the, you don't have to do that now, but if you head over to your inbox and you look at the email that Arif sent out, the picture was a projection of E8 onto its Coxeter plane. So I wanted to include a picture, but I've done something better. I've included a QR code. And there's actually this guy called Tamas Torba, who's basically done this, who's created some beautiful works of art using the root systems of G2, F4, E6, E7, and E8. And in a second, I'll tell you about exactly why those specific ones were used. And the pictures are really quite nice. So you can either look at this, you can either scan this and then navigate that website. You can go to tamasgorba.com, you just have to change this E8 to G2, F4, E6, or E7, and you'll get those ones. The final thing that I want to talk about is classifying semi-simple Lie algebras over C. And then you'll be able to hopefully see some of the relationships with Coxeter groups. So you have this thing called the Cartan decomposition, named after the French mathematician Émile Cartan, where if you have a semi-simple Lie algebra over C, over the complex numbers, you can decompose it in this manner. This is just direct sum decomposition. Lie algebra fundamentally is a vector space with a bunch of other things. And these are just subspaces. Okay, you don't need to know any of this. You don't need to understand any of this. I've included more for my own satisfaction. And this, I know that plenty of people will be able to appreciate this. But the cool thing is that phi over here is a root system. Okay. So remember how I said there are multiple ways of defining root systems. This is once you can define it using a bunch of axioms, and you can show that actually phi satisfies all of those axioms. So these guys, alphas, right? These are actually vectors. They live in the dual space of this H thing. Okay, so they're essentially vectors. And therefore, because it's a root system, the classification of root systems, which we have seen in this talk, gives you a classification of complex semi-simple Lie algebras. Moreover, you have this fact that a semi-simple Lie algebra over the complex numbers is simple if and only if the associated root system is irreducible. And we have seen the classification of irreducible root systems in this talk.
Will
right? So you have some cool facts over there. So this is a list of the complex and simple algebras. Yeah, I think I should also include a crystallographic edition, but yeah. So this is why you didn't see a CN in any of the previous slides. If that makes sense. You might have noticed there was an AN, BN, and a DN. The reason why you didn't have a CN is because CN and BN are almost the same thing. The only difference is that when you represent, these look like Coxeter graphs, but these are called Dayton diagrams. There's a subtle difference between Dayton diagrams and Coxeter graphs. So it's not the number of bars, because the number of bars corresponds to the number that we were talking about. So if you have 2 bars over here, that corresponds to having a 4. 3 bars corresponds to 6, and so on. But rather, the interesting thing is the direction of these arrows, because the arrows go from long roots to short roots. If you have the CN and BN, the difference is the length of the roots. That makes sense. Now, finally, what makes G2, F4, E6, E7, and E8 so special is we had someone who was talking about whether these root systems don't exist in dimensions higher than 8. And I pointed out that AN, BN, CN, and DN do. But the other ones don't. They are very specific to the dimensions they live in. So the first 4 are usually called classical. Like you talk about classical Coxeter groups, you talk about classical. You just add, if you add the word classical in front of them, it means that you're talking about something that's valid in all n of these dimensions. But these 5 are usually referred to as the exceptional group system, or the exceptional algebras, or the exceptional groups, because they only exist in these specific dimensions. In fact, my M5 project has something to do with the E8 group system. But yeah. So I think that's pretty much everything that I wanted to say. Does anyone have any questions? Yes.
What's the connection between the matrix you use to determine the Coxeter graphs and the Carter matrix? What was it supposed to
So remind me what the Cartan matrix is again. I forget the definition. There is a relationship between them. I think the Cartan matrix has to do with the basis rather than the angles.
Of the Coxeter, the matrices that are the matrices. Because I think you need to take down some integer values to force.
They're all integer values.
Yeah, but 4 is like too big, right? You make 2 or something.
Actually, no, the entries of the matrix are not integers. The entries of the matrix are the cosine or are the negative cosine of pi over pij. So those guys are actually going to be less than 1. They're going to be like between, like, you see?
Yeah. Yes. Yes, but
Because if I'm not wrong, I might be misremembering, but if I'm not wrong, the Cartan matrix has to do with the basis of these guys.
yeah, exactly. But the
Right.
structure is pretty similar. I think it's probably different from how we find these matrices.
Yeah, because the matrices that I was talking about are somehow they're used more for this positive definiteness thing. So maybe I should say a word or two about the classification process, right? So one of the things that you do is when you look at an irreducible Coxeter graph or a connected Coxeter graph, one of the ways. So first of all, you can show that if I have that list that I had up earlier, you can show that all of those Coxeter graphs are positive definite. But then you kind of want to show that those are the only possible positive definite ones. So to do that, you have to look at graphs and subgraphs and determinants of these subgraphs. The reason why you need to look at the determinants of subgraphs is because you would be using this Sylvester's criterion that I mentioned, which essentially looks at the determinants of minors of the matrix. So you can show that there is a correspondence between the minors of the matrix that I talked about and subgraphs of the Coxeter graph in question. So that's why that matrix is relevant. So I think the purpose is perhaps what distinguishes it from the Cartan matrices in studying the algebras. Does that answer your question? Okay, we can talk more afterwards if you like.
Don't take n to be a finite number. You consider the overall. An infinite space, but take the infinite point into a single
Infinite orthogonal group. Okay. I guess it would depend a lot on the space. What spaces do you have in mind? Because there's not one infinite dimensional pure vector space, right? Multiple infinite dimensional vector spaces over R, which have norms, and you then think about there's no infinite dimensional Euclidean space. I'm not sure. I'm not sure. Might be able to, I don't know, it might be possible to think about what happens in infinite dimensional spaces, but a priori, I don't know.
You have the representation. The representation.
Yeah.
Finite space.
They're finitely presented though. Like if you look at the Coxeter presentation, so I mentioned earlier there's a thing called Coxeter's theorem, which gives you, so that kind of defines what a Coxeter group is in an abstract sense. So I defined it in a very geometric and very concrete manner. But and then Coxeter's theorem is really a theorem, which gives you a characterization of these in terms of abstract groups. It gives you a presentation thereof. But you can also define a Coxeter group as being something that has such a presentation, and then you can show that it has geometric properties. And the key fact over there is that you view it as having a finite presentation, i.e. a finite number of generators and relations, actually. Yeah. Is that?
Yeah.
Yeah.
I'm quite confused about how to find a single root system can go back.
Sorry?
Single root system to how to find one.
Okay. Maybe it's easier if I exit and oh dear, now I can't see. Where's the mouse? This is where. Okay, there we go. I just have to click. Look at that. All right. Yeah.
I was trying a three-dimensional case that is just the symmetry of tetrahedral. So the
Three-dimensional case.
yes.
Okay.
So that should give me 12 roots there.
I don't see why not. Yeah.
Yeah, but how can I find a single root system? I tried that for attempts and I found that it didn't give me the custom diagram that you illustrated here.
Maybe I was wrong in saying that I5 is I could have been wrong in saying that I5 was the thing. Perhaps we can talk about this afterwards. Just if there's any more questions, are there any more questions? If not, I will head over there and have that conversation. All right. Okay. Thank you very much, guys, for having me.